You've seen the sun every day. You've watched the stars twinkle across the night sky, scattered like diamonds on a canvas of black velvet. Beautiful, familiar, yet when was the last time you asked yourself what's actually happening up there? What is a star actually doing? Most people, when asked, will give you the simple answer: burning. The sun is burning. It's a giant ball of fire. But that's wrong. Completely wrong. Fire is a chemical reaction, and space has almost no oxygen. So no, the sun isn't burning like you think it is. This answer doesn't just miss the mark, it misses the entire point. Let me break it down. Okay, you've heard the real answer: nuclear fusion. The sun is powered by nuclear fusion. Hydrogen atoms fuse into helium, releasing energy. That's the textbook explanation, the quick fix. But can you explain what that means? Why do hydrogen atoms fuse? What forces them together? What actually happens when they do? Or are you just repeating words you've heard, much like a parrot says hello, without understanding what a greeting really is? If you can't explain that process, you don't understand how stars shine. You only have a label. And labels don't mean understanding. They're a way to mask our ignorance. We use them as shortcuts, hoping they'll answer questions without us having to dig deeper. So, let's stop using labels and dig into the real answer. What is happening inside stars? Why do they shine? And why is this so important for everything you see, feel, and experience on Earth? Let's start with something tangible. Picture holding a tennis ball. Squeeze it in your hand. You feel the pressure. It compresses just a little bit, right? Now, imagine a mountain, a massive one, like Mount Everest, sitting on top of that ball. The pressure would be unimaginable, and the ball would be crushed flat. That pressure is exactly what's happening at the core of the sun. But the sun isn't just any ball. It's a massive ball of gas, mostly hydrogen. When I say massive, I mean 99.8% of all the mass in our solar system is contained in the sun. Everything else, the Earth, Jupiter, the other planets and moons, that makes up just the remaining 0.2%. The sun is unimaginably heavy, and all of that mass creates gravity. The weight of the sun's outer layers presses down on its inner layers, and all that pressure builds as you move inward toward the core. The pressure at the sun's core is so extreme that it's hard to even comprehend. At the sun's surface, the temperature is about 5,500 degrees, but as we go deeper, the temperature increases layer by layer. By the time you reach the sun's core, it's 15 million degrees. The pressure, 250 billion times greater than Earth's atmospheric pressure. To put that into perspective, if you were to grab a chunk of material from the sun's core, about the size of a pinhead, it would weigh as much as a small car. So with all that mass gravity pulling everything inward, why doesn't the sun collapse? How does it maintain its shape and not implode? What is holding the sun up, resisting that immense pressure? The answer lies in the nuclear fusion happening deep within the sun. But let's pause for a moment. To understand what's really keeping the sun from collapsing, you need to know why fusion happens in the first place. And to understand fusion, you need to appreciate the physics that shouldn't allow it to occur. The sun is mostly hydrogen. Hydrogen atoms are very simple: one proton and one electron. But when you heat those atoms up to millions of degrees, the electron gets stripped away, leaving you with naked protons flying around. To make fusion happen, those protons need to get close enough for the strong nuclear force to bind them together. But there's a problem. Protons are positively charged, and like charges repel each other. So, the protons should be pushing away from each other, not getting close enough to fuse. The electromagnetic force is preventing them from coming together. The only way to get past this repulsion is to get the protons moving incredibly fast, to make them collide with enough force to overcome the repulsion. How do we make those protons move that fast? Heat. Temperature is simply the average speed of particles. The hotter something gets, the faster its particles move. So, the sun's core, with its 15 million degrees, should give the protons enough speed to collide at 500 km/s. But when you calculate how much energy those protons actually have compared to how much they need to overcome the electromagnetic repulsion, it turns out that at those speeds, they still don't have enough energy to fuse. The sun shouldn't be able to shine. And yet, here we are. Something is wrong with the way we understand how particles move. That's when quantum mechanics enters the picture, and things start to get strange. In the world of quantum physics, particles aren't like tiny billiard balls with set positions. Instead, they are probability waves. Instead of having a definite position, a proton has a range of possible locations. This is where quantum tunneling comes in, one of the most mind-bending concepts in physics. Imagine you're throwing a ball at a wall. In the regular world, if you don't throw it hard enough, it bounces back. But in the quantum world, the probability wave of the proton doesn't stop at the wall. It leaks through. Occasionally, the proton appears on the other side. This phenomenon is called quantum tunneling. The proton doesn't have enough energy to get through the electromagnetic barrier, but its probability wave extends through it, and sometimes that probability becomes reality. In the sun's core, this quantum tunneling is exactly what allows fusion to happen. Even though the protons don't have the energy needed to overcome the repulsion, they can tunnel through and end up close enough to fuse. The probability of tunneling is small, but when you consider the sheer number of protons in the sun, around 10^56 particles, those small probabilities add up. With billions of protons colliding billions of times per second, what seems improbable becomes inevitable. This is the real reason why the sun shines. This is how quantum mechanics makes fusion possible, despite the classical physics saying it shouldn't work. So now we have two protons that have successfully tunneled through the electromagnetic barrier. What happens next is just as strange. These two protons don't just stick together. One of them transforms. It stops being a proton and turns into a neutron. How? This transformation is caused by the weak nuclear force, the third fundamental force in play here. The weak force is responsible for transforming particles. It takes the proton and flips one of its quarks, changing the proton into a neutron. As part of this process, the proton emits a positron, the antimatter counterpart of an electron, and a neutrino, a ghostly particle that barely interacts with anything. Now you have a neutron and a proton bound together. This is deuterium, or heavy hydrogen, the first step in the fusion process. But we're not done yet. This deuterium nucleus is unstable. It craves more protons to fuse with, so it quickly collides with another proton. The strong nuclear force binds all three particles together, creating helium-3, but we still aren't done. Helium-3 is still not stable enough to stop the process. The core continues to churn, and helium-3 nuclei, forged in separate fusion reactions, eventually meet. When they do, something elegant happens. The nuclei collide and merge, forming a new nucleus. This combined nucleus has 4 protons and 2 neutrons, but it's too heavy. The nucleus spits out 2 protons, and what's left is helium-4, the kind of helium that's found in birthday balloons. At this point, the fusion process has formed the most stable element, helium-4. Now, let's step back for a second. This all started with 4 protons, 4 hydrogen nuclei. But through a series of collisions, transformations, and fusions, those 4 protons became 1 helium nucleus. And if you weigh these 4 protons and compare it to the mass of the helium-4 nucleus, you'll notice something startling. The helium-4 is lighter than the 4 protons that created it, about 0.7% lighter. Where did that mass go? This is where Einstein enters the picture. You've heard the equation. Everyone has E enter mc2. Energy equals mass times the speed of light squared. It's famous. It's on t-shirts and it's even tattooed on people's arms. But what does it actually mean? It means that mass and energy are 2 forms of the same thing. They are interchangeable. A little bit of mass can be converted into a tremendous amount of energy, and that's exactly what happens when stars shine. That 0.7% of missing mass didn't disappear. It transformed into energy. The fusion process produces energy in the form of photons, neutrinos, and kinetic energy. The sun's core is converting mass into energy every second. And when you consider the enormity of the process, it's mind-blowing. Every second, 600 million tons of hydrogen are fused into 596 million tons of helium. 4 million tons of mass are converted into energy every second, non-stop, continuously, for billions of years. This constant release of energy is what keeps the sun stable. But here's the big question. What keeps the sun from collapsing under its own immense gravity? The answer is the energy released by fusion. The process of fusion generates radiation pressure, which pushes outward. Every fusion reaction is like a tiny explosion, and billions of these reactions happen every second. This creates an enormous outward force, pushing against gravity, which is constantly pulling everything inward. For most of the sun's life, gravity and fusion are in perfect balance. Gravity pulls inward, while the energy from fusion pushes outward. This balance allows the sun to shine for billions of years. But this balance doesn't last forever. Eventually, the core will run out of hydrogen to fuse. When that happens, fewer fusion reactions will take place, and gravity will begin to win. The core will contract, which will heat it up even more, leading to the fusion of helium into heavier elements like carbon, oxygen, and silicon. This process will continue until the sun starts fusing iron, which marks the end of the line for fusion. Iron is the heaviest element that can be fused in a star. When the sun's core turns to iron, fusion will stop. At this point, there won't be anything pushing outward anymore. Gravity will take over completely, causing the core to collapse in a matter of milliseconds. The outer layers of the sun will crash inward, causing a massive explosion, a supernova. This is the final act of a star's life, an explosive death that scatters heavy elements like gold and uranium into space, seeding the universe with the raw materials for new stars, planets, and even life itself. In this explosion, heavier elements are formed, and the remnants of the star's collapse create the building blocks for everything we see and feel on Earth. The calcium in your bones, the iron in your blood, all of it was created in a star that died long before our sun was born. You are literally made of stardust. And it all began with fusion, atoms fusing to create energy. The process that powers the sun and stars is the reason life exists. Everything we know, every molecule, every cell, every living organism, traces back to the energy created in stars. You've seen the sun every day of your life. You've looked up at the stars on clear nights, thousands of them scattered across the sky like someone spilled light across black velvet. Beautiful, familiar. But have you ever actually asked what's happening up there? Not poetically, physically. What is a star actually doing? Most people, if you press them, say burning. The sun is burning. It's a giant ball of fire. Wrong, completely wrong. Fire is a chemical reaction. It needs fuel and oxygen. You know what? Space has essentially none of oxygen. The sun isn't burning any more than your refrigerator is burning. That answer doesn't just miss the mark. It misses the entire universe. The mark is in. Okay, fine. You've heard the real answer. Nuclear fusion. The sun is powered by nuclear fusion. Hydrogen atoms fusing into helium. You learned that somewhere. Maybe school. Maybe a documentary. But here's my question for you. What does that actually mean? Can you explain it? Can you tell me why hydrogen atoms would fuse? What forces them together? What happens when they do? Or are you just repeating words someone told you the same way a parrot says hello without knowing what a greeting is? Because if you can't answer those questions, you don't understand why stars shine. You just have a label, and labels aren't understanding. Labels are what we use to hide our ignorance from ourselves. We say fusion and nod and move on as if naming something explains it. It doesn't. The real answer to why stars shine involves gravity so intense it defies imagination. Quantum mechanics so strange it breaks your intuitions about reality, and a force powerful enough to vaporize entire cities released continuously for billions of years. And here's the part that should stop you cold. That process, that incomprehensibly violent reaction happening 93 million miles away, is the only reason you exist. Every breath you take, every bite of food, every heartbeat, all of it traces back to what's happening inside stars. So maybe it's worth understanding, really understanding, not just labeling. Let's start with something you can feel. Hold a tennis ball. Squeeze it. You can compress it a little. Right now imagine a mountain sitting on that ball. Not a small mountain, Everest. Millions of tons of rock pressing down. The ball would be crushed flat, obviously. Now multiply that pressure by 1 billion. That's what's happening at the center of the sun. A star is a massive ball of gas, mostly hydrogen. And when I say massive, I mean the sun contains 99.8% of all the mass in our solar system. Everything else, Earth, Jupiter, all the planets, all the moons, all the asteroids, that's the remaining 0.2%. The sun is unimaginably heavy, and all that mass creates gravity. Every part of the sun pulls on every other part. The outer layers press down on the inner layers. The inner layers press down on the core. Layer after layer after layer. All that weight accumulating, squeezing, crushing inward. At the surface of the sun, things are hot, about 5,500 degrees C. But go deeper. Push through hundreds of thousands of kilometers of solar material, each layer heavier than the last, each layer pressing down harder. By the time you reach the core, the temperature is 15 million degrees. The pressure is 250 billion times the atmospheric pressure on Earth. Let me say that again. 250 billion times. The density is so extreme that a chunk of core material the size of a pinhead would weigh about as much as a small car. Now, here's the question that should be bothering you. With all that weight, all that pressure, all that gravity pulling inward, why doesn't the sun collapse? Seriously, think about it. You've got this enormous ball of gas, and gravity is pulling every atom toward the center as hard as it can. What's stopping it? Something must be pushing back. Something must be resisting that unimaginable inward pressure. If nothing pushed back, the sun would collapse in about 20 minutes, just crumple in on itself. But it doesn't. It's been sitting there stable for 4.5 billion years. What's holding it up? Here's where things get strange. To understand what's pushing back against gravity, you need to understand fusion. And to understand fusion, you need to see why it shouldn't happen at all. The sun is mostly hydrogen. A hydrogen atom is simple. One proton, one electron. Strip away the electron, which happens instantly at millions of degrees, and you're left with naked protons flying around. For fusion to occur, two protons need to get close enough to stick together. And by close, I mean close. They need to be within about 1 femtometer of each other. That's 0.001 m. At that distance, the strong nuclear force grabs them and fuses them together. But there's a problem, a big one. Protons are positively charged. And what do like charges do? They repel. Remember the electromagnetic force from earlier? The one that's 10 to the 42nd power times stronger than gravity? That force is screaming at these protons to stay apart. As two protons approach each other, the repulsive force between them grows enormously. It's like trying to push two incredibly powerful magnets together, North Pole to North Pole. The closer you get, the harder they push back. So you need energy to overcome that repulsion. You need protons moving fast, colliding hard, forcing their way through the electromagnetic barrier. How do you get protons moving fast? Heat. Temperature is just the average speed of particles. Higher temperature means faster particles, more energetic collisions. The sun's core is 15 million degrees. That's hot. That should be enough, right? Wrong. Here's the calculation that broke physics in the early 20th century. At 15 million degrees, protons are moving fast, about 500 km/s. But when you do the math, when you calculate how much energy those protons actually have versus how much they need to overcome electromagnetic repulsion, they come up short. Way short. The protons in the sun's core have only about 1/10 of the energy required to get close enough to fuse. Classical physics says those protons should just bounce off each other every single time. Fusion shouldn't happen. The sun shouldn't shine. You shouldn't exist. And yet here we are. Something is wrong with our understanding. Or rather, something is missing. The missing piece is quantum mechanics. And it's going to violate everything you think you know about how objects move through space. In your everyday experience, particles are like tiny billiard balls. They have definite positions. They travel in straight lines until something deflects them. If there's a wall in the way, they bounce back. If they don't have enough energy to climb over a barrier, they don't get over. Simple, obvious, and completely wrong at the quantum scale. Particles aren't little balls. They're probability waves. An electron, a proton. These things don't have exact positions until you measure them. Instead, They have a probability of being in various places. The wave function, as we call it, describes the likelihood of finding the particle at any given point. And here's where it gets weird. That probability wave doesn't stop at barriers, it leaks through. Imagine you're throwing a ball at a wall. In the normal world, if you don't throw hard enough, the ball bounces back every time. But in the quantum world, if you throw enough balls, occasionally one of them just appears on the other side. It doesn't break through. It doesn't go over. It doesn't have a secret tunnel. It simply has a non-zero probability of being on the other side. And sometimes that probability becomes reality. We call this quantum tunneling. And it's not a metaphor. It's not an approximation. It's how the universe actually works. Back to the sun. Those protons don't have enough energy to overcome electromagnetic repulsion. Classically, they should bounce off each other. But they're not classical objects. They're quantum objects, and their probability waves extend just a tiny bit through the barrier, which means occasionally two protons tunnel through the repulsion and end up close enough for the strong force to grab them. Is it likely for any individual proton? Absolutely not. The probability is absurdly small. But how many protons are in the sun's core? About 10 to the 56th power. When you have that many particles colliding billions of times per second, improbable becomes inevitable. Quantum tunneling is why the sun shines. The universe has a cheat code and stars exploit it.